In this presentation, we will discuss how to use the launcher tool in order to compute wavelets for less input. The first thing we need to do before actually running the wavelet analysis algorithm, we need to filter the last input file, because the file can contain duplicates or irregular or degenerate points that may lead to numerical instabilities. It needs to be subjected to a noise suppression filter first of all. Let's see this example on this file, which is a segment of a fragment of the Hawaii mountains in the Hawaii range. So this is the point cloud that will constitute the input of our algorithm. You can observe that there are some points here that are above ground corresponding to vegetation classes, mainly palm trees, and we will need to project these points on the surrounding ground soil level, because that's how the algorithm works, by treating classes as additional channel attribute components of the X, Y, Z points in the original input. Let's quickly examine the contents of the launcher release folder. One of the important files here is the launcher config XML file containing some important parameters that the application will need in order to function correctly. This is an XML file which contains the following sections. You will need a distribution of the last tools, set of tools, which is provided with this release package, and you'll have to set the folder path to the bin folder of the last tools. Then you will need to set up a temporary working folder in which the intermediate results of the last filtering process will be stored in, and you can later proceed in examining what has been generated in there in order to find faults or errors in the last processing algorithm. Then you will need to point towards the python.exe interpreter executable. You'll have to use Python 2.7, and typically this is the path where the Python distribution installs this executable. Last, you will have to specify the path to the scripts folder that are used in the processing of the last of the raw input last files that you need to filter before actually computing the wavelet data or the filtered wavelet data. Let's run the launcher executable application, and the GUI of our application is rather simplistic, and its only purpose is to facilitate running the processing scripts or the wavelet analysis synthesis executable file with correct command line arguments. Let's first examine the preprocessing procedure, which is going to be launched from this left pane. We have a first input containing the maximum point count per last file. This is due to a limitation in the liblast tools, as they cannot process files that are more than, if I remember correctly, 1 million points per input file. So we will have to split the last files into smaller chunks that we process individually, and then we will merge those files back into a filtered output that contains unique points, so no point duplicates in the XY ground plane. Also, the vegetation points are projected on the ground level locally, and furthermore, any noise is also removed from the data. Let's now see the application in action. Let's filter this kawaii fragment. Now Python will run in the background if you have set the right paths, and now we are prompted with the fact that an output has been written in the temporary folder. It's in a binary format containing the filtered point cloud. The output, as stated before, is in binary format, but still the application is able to produce the final stages of the processing in last format, which we can now view. And as we can see, the previously vegetation points were projected on the ground, and noisy points were removed altogether from the input point cloud set. This point cloud is was further processed with Python in order to produce the raw binary BPC format, which we can now use further to produce a triangulation or a thin accompanying triangulation file or mesh. We will do this using MATLAB. In the external scripts folder of your release package, you will find a MATLAB script that we can use in order to produce the triangulation of our raw binary point cloud. The script named filter BPC takes 3 arguments. The first command line argument is the path to the raw point cloud, and the output will be again a filtered binary point cloud file containing only those points that could be triangulated by MATLAB into a nice terrain mesh. And the second accompanying file for now contains the indices pointing towards the points in this output binary point cloud, actually revealing the triangles that are part of the final mesh that we can use for the wavelet analysis. Thus we can run the script, and at least for small files we can see that the runtime is rather small, and here are our binary pairs of point clouds and triangulation data that we can use for the wavelet analysis. And now we can launch our tool to produce let's say 4 levels of cascaded wavelet coefficients are also going to be stored in specific binary formats. In an output file, we'll name this output file kawaii wavelets .dat, and one little constraint that we need to take into account is the fact that the input BPC or B10 must have the same file. So if we have a kawaii final BPC and a kawaii nothing B10, the application will complain that it cannot find one of the 2 files. So let's use the BPC for reference, and it will automatically fetch the B10. And let's launch the wavelet application analysis application. Okay, so that was quite quick, and you can see the rendered output. You can move around using rotate using the mouse click button and WASD keys and Q and E keys to translate around the input model. Whenever you are ready, you can press, or you'll have to press the O key in order to produce the output file kawaii wavelets dat. In the background command line, you will see what the magnitudes of the difference vector average, what the average difference vector magnitude is, and how many points were part of each cascade of analysis. You can see that the kawaii wavelets that has been written to your temporary folder path, and it's ready for the next stage, which is the wavelet synthesis and nonlinear min shift filter. As for the first analysis stage, we will have to specify an output file name for the filtered data, and we can use the output of the analysis stage as input for this stage. We will select the dat file, and for the Riemannian mean shift algorithm, we have several parameters. We will set the spatial bandwidth to 3, average edge lengths. This is thus specific for your input model. It's proportional to your average edge length in your input triangle soup. Then the range bandwidth, this is mostly useful for filtering the attribute classes and height above ground channels. Let's set that to 0.5. The epsilon is an iteration error telling the nonlinear mean shift algorithm when to stop, when it thinks it has reached convergence. It's also proportional to the average edge length, so I will set this a little bit higher to 0.1. The window size is the partisan window used by the nonlinear min shift algorithm. It's again proportional to the average edge length. Let's set it to 7. The maximum number of iterations of the algorithm before it decides to stop regardless of the epsilon error. Let's set it to 50. And the blurring passes, meaning how many mean shift passes will be the lowest level of the wavelet analysis stage. Let's apply 5 passes. And the detail vector factor is a factor scaling the detail vectors, or the wavelet coefficients in this case, and tells you how much of the original input details will be still present in the filtered output. Let's use a factor of 0.5, and let's run the application. We can see in the command line output several pieces of information regarding the statistics of the algorithm. The nonlinear mean shift algorithm is typically time-consuming, and so we will not be able to see that easily the output. Now, the output of the nonlinear min shift is visible, as in the first case, by navigating with the WASD keys and rotating with the mouse. You can see that this is a point cloud and doesn't have any triangulation information. Using the multiply and divide symbols, you can navigate between the levels of detail, and using the O key you can generate the output file.